Hello, I'll be making this short video on bond enthalpies. You'll need your homework packet, your class packet, and your blue reference tables. All right. Bond enthalpies, an easy lesson for today. The two equations you're going to be using are right here on the cover of your blue reference sheets. It's important that you're comfortable using both of these. Of course, you have already used the enthalpies of formation with last night's homework. Here's the new one, BE for bond enthalpies. This equation is saying that the bond enthalpies of those bonds that are broken are written down, and you subtract the bond enthalpies of those bonds that are made. Now, it's very important that you know which bonds are broken and which bonds are made. Here in the enthalpies of formation equation, it specifically tells you that the products come first and the reactants come second. That is not given to you in the bond enthalpies equation. You have to know that bonds broken are the reactants and that bonds made are the products. If you look at page 14 and then page 16, I have two visuals to help you understand the arrangement of these terms in the two equations for heats of formation and bond enthalpies. If these visuals are of no help, don't worry about it. You do need to know the definitions. The enthalpy of formation is the energy to form 1 mole of a compound from its naturally occurring elements in their standard states. Bond enthalpy is the energy to break 1 mole of bonds in gaseous molecules under standard conditions. Please note the subtle differences between these two definitions. To use your heats of formation, you go to your reference tables and notice it's just one column in this thermodynamic data that you will be interested in. Notice that all of these values are given in kilojoules per mole. The equation is not given to you. You have to write the equation that represents forming 1 mole of these compounds from their elements in their naturally occurring states. And notice that these energies are both positive and negative. Now, the bond enthalpies are also in your blue reference tables, but I want you to notice that the bond enthalpies are always positive. Also, don't confuse this table with the table on the previous page that's called bond lengths. The tables look very similar. Read the title. These are the bond enthalpies. This is the energy per mole to break 1 mole of carbon-bromine bonds. Here, if I go to H right here, this number 436 is the number of kilojoules per mole of diatomic hydrogen molecules to break that 1 bond in between the mole of hydrogen molecules. If you're breaking double and triple bonds, those bonds are here at the bottom of the chart. Now, this visual might be of help, but what I'm pointing out is with the heats of formation equation, you start with the heat of formation of the products and you subtract the heat of formation of the reactants. It's because of the definition of the orientation of this energy change. Whereas on page 16, where I have the visual for bond enthalpies, the orientation of this bond enthalpies is that to break bonds, which is what you do to reactants, is what the number represents. So here you have bond enthalpies of reactants representing broken bonds, and then you have to negate that value to represent the bonds that are formed. Now, this sample is on page 17 of your class packet, and I want to go through it with you. You have a balanced chemical equation. Remember, the goal of this whole chapter is to find the heat of the reaction. What is the specific amount of energy that goes with this combustion reaction of methane? We can do it with calorimetry. We can do it with heats of formation. And now we're going to do it with bond enthalpies. The important thing to remember with these double stars is that you should see the bonds that you're breaking and making. So draw the structural formulas. When you look at methane, you can see that there are 4 CH bonds. When you draw the 2 molecules of oxygen that are reactants, you remind yourself that those are double bonds between the oxygens in the diatomic molecules. When you make the CO2, you remind yourself that those are double bonds and the 2 water molecules. So the equation is the bond enthalpies broken, which are right here. There are 4 CH bonds that are broken. 4 CH bonds that are broken. And it's the sum of plus the 2 double bonds between the 2 oxygen, within the 2 oxygen molecules. So that's 2 times that double bond enthalpy. Now we move to the products, the bonds that are being made. That's why you have to change the sign. You've got 2 C to O double bonds, and you've got 4, 1, 2, 3, 4 O to H bonds. When you set that up, reminding yourself what the number is and what the number of bonds are, you get the answer. I prefer setting it up this way myself, using an equation, but some people prefer to use a table. So once you, sorry that you can't see this. Once you do this equation, substitute in the numbers and do the math, -808 kilojoules per mole. Now, next one, page 17. Estimate the energy change that accompanies the following reaction. To take hydrogen and fluorine as a gaseous molecules and make HF. You have to write the balanced chemical equation. You have to see those bonds. Remember that bonds broken minus bonds made is the equation. Now, sometimes people like to go ahead and write down these bond enthalpies so that you don't have to go back to the table anymore. Write them down. And then look at the structural formulas. You've got 1 mole of H to H bonds being broken as a reactant, 1 mole of F to F bonds being broken, and 2 moles of H to F bonds being made. If you do the math, the enthalpy would be -539 kilojoules. Now, sometimes you don't have to make and break all the bonds. And I'll point this out to you. If you want to do all the bonds, you'll never be wrong. But it is more likely to make a mistake the more bonds that you unnecessarily break and make. Look at this equation. Propene, which is 3 carbons with a double bond in it, can be reacted with hydrogen to make propane. So here's the reaction. It's a 1-to-1-to-1 balanced chemical equation. Your goal is to find the enthalpy of that chemical reaction. Double stars. Look at these 3 formulas, the structural formulas. Here is the propene molecule, the hydrogen molecule, and the propane molecule. If you look at where my red arrows are, you're really only breaking the double bond here in this propene molecule. You're only breaking the bond between the HH here. And the 3 bonds that you're making are these 3. No other bonds need to be involved in this calculation. So here I am specifying only looking at those couple of bonds that I'm breaking, the double bond C, the H to H bond, those are my bonds broken, and the bonds that I'm making are 1 carbon to carbon bond and 2 carbon to hydrogen bonds. I take those 2 numbers, take the bonds broken minus bonds made, and I get my enthalpy of the reaction as written. You can try it here on page 18. Here's acetone, and I've drawn the structural formula for you. Acetone, when it reacts with hydrogen, the diatomic molecule H2, it makes a molecule called isopropanol. Don't worry about these formulas. I'd make sure that you know them. You see, instead of breaking everything, which would be a pain, you're really only breaking that double bond and this single H to H bond, and you're making these 3 bonds. You try this. I'm going to pause, and you try this math. All right, I hope you've had a chance to finish the problem. So here you have the bonds broken and the bonds made. When you take those sums and put them in the equation, bonds broken minus bonds made, you would have 5 kilojoules for your answer. Red slide. You need to understand that breaking bonds is endothermic and making bonds is exothermic. You have to put energy in to break the bond, and you get energy given off when a bond is made. Next, red slide. Draw these structural formulas. If you want to see what bonds you're breaking, it's best to look at the molecules and see that you have double bonds sometimes, single bonds sometimes. Red slide. Remember that the heats of formation are values that can be positive or negative, but bond enthalpies are defined as the energy to break a bond. So bond enthalpies are always positive. There are some worked examples here on page 26 that I'd like you to do. These worked examples are asking you which of the following processes are endothermic, A, B, C, or D. Good concept question. Work example on in your book on page 187, but I've got it in your class packet. Another good one for you to work and check your answer here. I want you to skip this ozone problem and jump to page 19. I am showing you these 2 equations on the same page with these 2 visuals, just so that you can see what I talk about here with the arrows going up and down. Study these, ask me questions. On page 20, there are 4 problems that summarize 2 problems on heats of formation, 2 problems on bond enthalpies. Try it. You'll like it. And then check your answers on Schoology and let me know how I can help. Simple problem to solve, not as conceptually difficult as calorimetry. Thank you, and I'm glad you took the time to watch this video.